So hold on 1 second. So why is it not? Just give me a minute. Huh? There's some issue with the screen sharing.
Sure, no worries.
So the screen. Do you see anything? Do you see the presentation?
I just see a blue screen.
Yeah. So it's basically the same thing. Why is the presentation not showing up? Uh, so this is weird. For some reason, I cannot see my own screen. Let me try again. Okay, can you see the screen now?
So now I can see it.
Okay. Yeah. Okay. So finally that worked. So the section talks about digital logic design. When you talk about digital logic design, there are mainly two types of circuits in digital logic design: combinational circuits and sequential circuits, and some basic gates which also fall under combinational circuits. So the basic gates are your absolute primitives or primitive gates, and or not, NAND, NOR, etc. Right? So those are the fundamental, but those are still the fundamental blocks of any hardware design. And as you might have already studied the logic, ultimately it's all when you do chip design, and finally you get something working on a chip. Ultimately, on the chip, bottom line, everything is on transistors. Everything with the current technology, everything is CMOS transistor based. So based on which technology you're using, there might be millions and millions. And right now, if you look at it, a few billion transistors on a CMOS IC with the current technology out there. So the gates that you see here are ultimately are converted to transistors, and the transistors is what work on the bottommost part of the chip. But gates and a few other circuits are our fundamental blocks of digital design. And then we'll see how to use Verilog to design various circuits. So these are some very basic gates that I will not go through it one by one, but there's just basic gates that you already know: AND gate, OR gate, NAND gate, inverter, NAND, NOR, XOR gate. On the right hand side, you'll see the truth table for these two input gates. Right? For example, XOR gate, if the both inputs are different, output is 1. If both inputs are same, output is 0. So you would need to, if you have not done, I can share later on a ebook with you, or you can also Google it for that matter. You can quickly refresh this digital logic concepts after we go through, because of
I've done this in undergrad.
undergrad. Yeah. Yeah, see what happens is that's why I mean, and after a few years you tend to forget a few things, not like this, but maybe something later on. So if you quickly refresh that, it will be helpful for you. So the basic gates represented as symbols, as truth tables. These are the functions. As we already know, NAND gate is a universal gate, so any other gate can be constructed using a NAND gate. Any other basic gate, and NAND or and not OR gate. Similarly, NOR gate is also a universal gate. Any other gate, OR gate, NOT gate, AND gate, can be constructed using a NOR gate. So NAND and NOR are universal gates. These are some standard chips available in the market. These are ASICs, so you cannot change the functionality of these chips. These are basic chips with OR gates or NOR gates and AND gates built into it. Multiple such gates into a single chip, which you might have used at your undergrad level, building a circuit out of it. The integration of chips started at a very small scale level, a few gates, then it moved to hundreds of gates, then thousands of gates, and nowadays it's millions of gates and billions of transistors. So, but it started out as small scale integration, then we called it medium scale integration, then large scale, very large scale. So the terminology stops at VLSI. So even though we have millions of gates and billions of transistors, we still call it VLSI design or VLSI methodology of design. Combinational circuits. So as we saw, there are mainly two kinds of digital circuits: combinational circuits and sequential circuits. Combinational circuits are one where output is the function of current input, and there is no memory, or there is no any memory or any last value being involved. The current input generates the current output based on the function of the circuit. It provides a higher level of abstraction compared to transistor design. So gates are one level above CMOS transistor design, and then Verilog language, designing using a language, is one level abstraction above gates. So this combinational circuit has had advantage over CMOS design. There are various examples of combinational circuit. First is the multiplexer. Now here this is a 4 input multiplexer. A multiplexer is a combinational circuit where you have 2 raised to n data inputs. Depend if there are 4 inputs, there are 2 select lines and 1 output. And this is the functionality of a multiplexer. If select lines are 0 0, I0 will get passed on to the output. If it is 0 1, I1 get passed on, input 1 goes to output. If it is 1 0, I2 goes to output, 1 1, I3 goes to output. This is how a 4:1 multiplexer works. You have 2 raised to n number of inputs, n number of select lines, and a single out. Uh, Similar to 4:1, there might be other multiplexers like 8:1. If it has 8 inputs, then it needs 3 select lines. 2 raised to 3 is 8 inputs, so 3 number of select lines are required. So let's assume that there are two mux implementations. There are two outputs, F1 and F2. And if this is the combination of inputs given, what is the output uh, going to be generated? So I think there is an example somewhere after this slide. Yeah. Okay. So if you consider the F1 output, if ABC is 0, 0, 0, output is 0. If ABC, these are my select lines. If ABC is 0, 0, 1, output is 0, 0, 1, 0, 0, 0, 1, 1, 1. So there is a way where you can optimize your design, your logical design. Now this will be implemented using a 8 is to 1 mux. So can I optimize my design using a smaller circuit, or can I implement the same logic using a smaller circuit? So if we combine this or if you group this input combinations where ABC, where A and B, if they are 0, output F1 remains 0 irrespective of the C value. If A and B is 0, 1, irrespective of the C value, it follows the C value. F1 output follows the C value. 0, C is 0, F1 is 0. C is 1, F1 is 1. When A and B is 0, 1. Same is the case when A and B is 1, 0. When A and B is 1, 0, output F1 follows C input. So I can say F1 is equal to C when A and B are 1, 0. When A and B are 1, 1, F1 remains 1 irrespective of C value. So when A and B are 1, F1 remains 1. So this 8 input combinations can be optimized to 4 input combinations. Now this can be implemented as using a 4 is to 1 multiplication. So A and B 0, 0 means the zeroth input will go to output F1. So output F1 will be 0. So 0 is connected to I0, input 0. 0, 1, C, I1 will go to F1. In case of select lines AB 0 is 0, 1. So I1 is connected to C. 1, 0 select line, again C will go to output. So again I2 gets connected to C, and when A and B is select lines are 1, 1, output is 1. So 1 is connected to I3 input, which will go to output in case A and B select lines is 1, 1. So this 8 input design or a 8 input multiplexer got built to a 4 input multiplexer design. This is how you can manually optimize the design, or there are various ways later on which at the synthesis level also this gets optimized automatically after the simulation part is over. So demultiplexers are reverse of multiplexers. There is a single input. There will be 2 raised to n outputs and n number of select lines. So depending on the select line, one of the output goes high. The input goes to one of the outputs basically. So this is the reverse of multiplexer. One input, 2 raised to n outputs and n number of select. It has to be represented at a gate level. This is the gate level representation of. We have decoders. The next combinational circuit is a decoder, where depending on decoder is n number of inputs, 2 raised to n number of outputs. There are no select lines, just n number of inputs and 2 raised to n number of outputs. So depending on the input combination 0, 0, 0, 1, 1, 0, 1, 1, one of the output goes high. When input combination is 0, 0, O 0 goes high. Input combination is 0, 1, O 1 goes high. 1, 0, O2 goes high. If it is 1, 1, O3 will go high. Output 3 will go high. This is how a decoder works. You have n number of inputs and 2 raised to n number of outputs. This is a truth table given to you, and if we are asked to implement this logic using a decoder, how do we go about it? So now there are 3 inputs, so we need a 3 is to 8 decoder for that. Uh, 3 inputs. This is the the logical table that is given to you to be implemented. So some output is high. In case A, B, C, C in 0, 0, 1, that is 1, 0, 1, 0, which is 2, 1, 0, 0, which is 4, and 1, 1, 1, which is 7. So sum will be high when input combination is overall it is 1, 2, 4, and 7. So if you take the outputs O1, O2, O4 and O7. And if you OR them, if you connect the OR gate, you get a sum out. So if input combination is any of this, some output will go high. Similarly, C out, carry out will be high when input combination is 0, 1, 1, which is 3, 1, 0, 1, which is 5, 1, 0, which is 6, 1, 1, 1, which is 7. 3, 5, 6, 7. So O3, O5, O6, and O7 outputs. If you OR them and you get the output that will be represented by your C out. So uh, this logical table that is given to you, input table, can be implemented using a 3:8 decoder with a few additional gates. So we can build circuits like this. So typically you can you will be given either I mean this is a design specification for you. It's very small, but this is a design specification given to you, which is of a full adder circuit. So you can build that using a decoder logic also, if it is required. Okay.
Okay.
Reverse of decoders are encoders where you have 2 raised to n inputs and n number of outputs. So if there are 8 inputs, there will be 3 outputs. If there are 4 inputs, there will be 2 outputs. And encoder will act exactly reverse of decoder. So depending on which input is high, your output will be encoded. So if it's let's say 3 is to 3 encoder, and your in this case, let's assume output one is input one is high. So if input one is high, the output will be 0, 0, 1. It's a 3-bit output. If input 4 is high, it will be 1, 0, 0 encoded output. If input 7 is high, the output encoded output will be 1, 1, 1. So it's a binary representation, binary encoded output based on the input which goes high. That's a normal encoder. Then you also have something called priority encoders. Priority encoders, in normal encoders, only one of the inputs can go high at a time, not more than one input. In case of priority encoders, you can have more than one input going high at the same time. But the priority is assigned to, or importance is assigned to inputs in a particular manner or in a particular way. So let's say you have 8 inputs, I0 to I7, and let's say zeroth input has the maximum priority, uh, input 7 has the lowest priority. Let's assume that is how it works. And if let's say input 1 and input 5 is high at the same time, so it cannot be that your encoder output can be 0, 0, 1 and 1, 0, 1 at the same time. Input 0 has the highest priority, input 7 has the lowest priority in that order. So the highest priority I0 is not active. The next priority is I1, that is active. So I1 is active and that will be taken and output will be 0, 0, 1 in that case. Later on, when I1 becomes deactivated, then I5 will be considered in that case, assuming no other input has gone higher at the same at that time. So because I5 has a lower priority compared to I1. So we can have more than one inputs high at a time. Depending on the priority assigned to the inputs, your output will be based on the priority of the inputs. Any questions there for priority encoder? You understand that?
Yeah, I understood.
Then we have simple comparators. You can do the simple comparisons like equal to, greater than, less than, greater than, equal to, less than. Typically, comparators are built using XOR gates due to the XOR gate truth table. So this is a comparator circuit which will test whether A is equal to B. A is 4 bits, B is 4 bits. You can check if both are equal, XOR gate output is 0. So that's how it works. You check for the equality comparison. Same can be built using the other comparator operations like greater than equal to less than equal. Then you have adders, which is used for addition, and also used for multiplication specifically. Subtraction and division we can use dividers, but adders can be used for multiplication purpose. There are two kinds of adders. One is a half adder, the second is a full adder. Half adder is a circuit where you have two inputs A and B. There are two outputs, sum and C out. 0 plus 0 is sum 0 with carry out 0. 0 plus 1 is sum 1 with carry out 0. 1 plus 0 is 1, sum 1 will carry out 0. And 1 plus 1 inputs will give me sum 0 and carry out 1. The simple half adder circuit. We present it like this because the sum works like a, if you look at it, it is a XOR gate truth table. Inputs are different, output is 1. Inputs are same, output is 0. See how it works like an AND gate when we represent that. So both inputs are high, output is high. So this can be represented as an AND gate. This is my half adder circuit, the basic gate level. Then we have full adder circuit where there are three inputs A, B, and carry in acts as a third input. So when two inputs are high at a time, depending on which two inputs are high, we'll get sum and carry out generated. So if only one input is high, sum is 1, carry out is 0. If two inputs are high, we get sum 0 and carry out 1. All three inputs are high, we get sum 1 and carry out 0. 1 plus 1 will give you sum 1 is carry out 1. And if you represent the sum equation, sum logic and the C out logic, this is the circuit that will get built for a full adder circuit using basic gates. So half adder, there are only two inputs without carry in. Full adder, there are three inputs with carry in. Both cases there are two outputs, sum and carry out. Can be represented as block format or this format, doesn't matter. So this can be represented as different circuits in different formats. If you look at a full adder circuit, the sum can have is represented by equation. So sum of a full adder circuit will be xin, which is there are three inputs x, y, and c in this case. Xin, XOR in y, XOR in c. Give me sum out. Carry output can be represented using the equation xi yi. Xy plus xc plus yc. So this equation will give me the carry out of a full adder. In this case, it's three input. The basic form of adder, now if you look at it, is a ripple carry adder. So here we have two inputs A and B. Each input is 16 bits, 15 down to 0. And each bit has, so adder is represented for each bit of the input. So A0 plus B0 will be done by the 0th stage of the adder. And A1 and B1 will be added by the first stage of the adder. And so on till 15th stage of the adder. Each stage of the adder has two single bit inputs, one carry in input and two outputs, sum and carry out for that stage. This is called a ripple carry adder because the carry out of the earlier stage becomes carry in for the next stage. The carry is rippled through the stages. And finally, the 14th stage output carry goes to C in a 15th stage and carry out of the 15th stage here. This is the final carry out of this adder. And then you get each 16 bit sum outputs, one single bit carry output. The carry is cycled or rippled through various stages. That's why it's called a ripple carry adder. In this case, it's a 16-bit adder. There are certain advantages and disadvantages for this kind of adder. So the disadvantage is that the adder will be slow in this case because to generate a carry here, I need to wait for the other 16 stages to be over. So there will be a delay by the time I will get this carry out generation, this final level. But one of the advantages is it's pretty simple to build and simple to understand also. So that's an advantage of a ripple carry adder, that it's pretty simple to implement. The disadvantage is that it will be slow in operation. So when you want to do high-speed design, you cannot work with ripple carry adders. You have to build something called, or you have to use something called carry look-ahead adders. Carry look-ahead adders are such that in this case, if you look at the ripple carry adder, the main problem situation is generating the carry output. Otherwise, some outputs are generated pretty much instantly. Carry output of each stage has to be propagated from one stage to other stage and final this stage. So if we can solve this problem, the carry generation problem, we can solve the problem of ripple carry adder. So we can do that using something called carry look ahead adder, where the carry of each stage is represented by an equation based on inputs for that stage, the previous stages here. So C0, which is a carry output 0 stage, can be represented as A0 and B0. Carry 1, which is the carry output of first stage, can be represented by this equation. So such we will have 16 equations for 16 carry outputs. So if we can implement those equations parallelly, we can get the carry output of each stage parallelly. So the problem of ripple carry adder, that there was a delay in carry generation, goes away. In such cases, we can use carry look ahead adder for high speed designs. So that's the advantage, that the delay goes away and it is faster in operation. But there is a negative for that, where obviously when you build these equations, you need to build it using gates. So there will be more complex circuitry involved, and overall there will be something that we call a logical overhead or area overhead on the design, where we need more gates in this case to implement the carry outputs of each stage. So when you look at a bigger design, when you work on very big designs, normally you don't work only with ripple carry or only with carry lookout adders. Normally there is some combination of both. For each block, you can set constraints that we can use ripple carry adder in certain cases where we don't need high speed design, or a design is relatively lower speed. In the high speed sections of your design, you can use carry lookout adder. So we can mix and match and get advantages of both adder circuits in that case. Ripple carry will give me less area. Carry lookout adder will give me faster speed but more area. You can mix and match the adder implementation for various stages of the design. Okay, any questions?
Nothing as of now.
Okay. So that was a quick refresher of combinational circuits of digital design. We will also look at the sequential circuit part of digital design. The sequential circuit part, now we have the basic sequential circuit we can look at is a flip flop. Flip flop is a latches and flip flop for that matter. So flip flop is a circuit which has can be represented by this truth table here. The difference between a sequential circuit and a combinational circuit is there is a memory component involved in a sequential circuit, where it will remember the last value that was remember the last value of the output that was saved, that was generated. So these are normal flip flops, SR flip flops or normal flip flops. This is clocked flip flops, where there is a clock involved for the flip flop. And then we also have basic latches and flip flops. Typically latches that we work with. Yeah, this particular latch has preset and clear. The latches that we work with typically are level sensitive devices, which work at the logic high or low level. Flip flops are typically triggered by clock edges. That's a typical difference when we work with clocks, latches, and flip flops. Uh, in FPGA design, we don't want a latch. We don't use a latch. We use flip flops everywhere. How and where, we'll see it later on. So there are various versions of latches and there is various versions of flip flop. In this case, this is a latch with preset and clear. So you can preset the value, output value to 1, or you can clear the output value if one of these inputs is high. Then you have D latches, something called D latches. There are only two states. If D is 0, output is 0. If D is 1, output is 1. This doesn't have a clock inbuilt. So latches will respond to level 1 and level 0. Flip flops are typically edge triggered. They will respond to the positive going edge of the clock or the negative going edge of the clock, depending on how your flip flop. If it's a positive going edge, it will respond to the positive going edge means logic 0 to logic 1. So this is the positive going edge of the clock. Negative going edge, this is logic 1 to logic 0. This is the negative going edge of the clock. So flip flop will either respond to positive going edge or the negative going edge of the clock. Latches will always respond to levels, logic levels. And that is why we do not want latches in our design, at least on FPGA. There are various kinds of flip-flops. Theoretically speaking, D flip-flop, JK flip-flop, toggle flip-flop, normal SR flip-flop. When you work with FPGAs, you only have D flip-flops available in the target technology library. So we only have D flip-flops to work with. The other kinds of flip-flops are not available as a part of the library. JK flip-flop or toggle flip-flop, etc. So clock period is another concept that you probably have learned and you might know already. Clock period is the minimum clock period that you need to make your sequential circuit work. Sequential circuits will always need clock periods or clock to work with, and the minimum clock period that you need for your sequential circuit to work is the combinational delay. In case now this is the circuit, let's assume the combinational delay of the circuit plus the setup time and the hold time of the flip flops. That's a bare minimum time you need for your clock period to make your circuit work. If your clock period is smaller than that value, your design will not meet timing in that case. So you have to work with various mechanisms to meet timing. The combinational logic delay, which is basically the propagation delay of various gates, the setup time of the flip flop and the hold time of the flip flop. If you add all of them, this is the bare minimum clock period you need to design. Any questions?
No, I've read this during my undergrad, so it's just a refresh. So
Okay.
I understand that.
There are various other kinds of sequential circuits which uses flip flops. So if we combine the flip flops, you get something called registers, which is basically flip flop represents one bit of data. You have multiple bits of data, you combine the flip flop and create a register. The normal register will look like this. So, and there is various different kinds of register, like shift registers. Shift register will either shift the data to right hand side or to left hand side. Now this is a bidirectional shift register with parallel load. So basically, bidirectional shift register means depending on the input, either it can shift the data to the left hand side or to the right hand side, and there is a parallel load. Load is the operation where all now in this case there are 4 bits of data. So all 4 bits, there are inputs I0, I1, I2, and I3 can be set to a particular value, and the output A0 to A3 will follow those values in case it's a load operation. There is no shift operation, it's only a load operation. The input values will be loaded and it will be sent to the output. In that particular part of the design, the shifting operation will not take place. Only the loading operation takes place. Input to output. In the other part of when the loading is not active, then the shifting happens either to left hand side or to right hand side. So there are various kinds of shift registers which will help us shift the data. Then we have counters to count the cycles. So depending on this is a 4-bit counter. So you can have different kinds of counters to count the cycles basically. So you need counters. You need all these circuits when you build bigger circuits out of it. You need registers, you need shift registers, you need counters to count clock cycles, to build timers out of it. At a basic digital circuit level, a counter works using flip flops. So the next part of a sequential circuit is memory. Right? Memory is a circuit which can help us store values, store data till it gets updated. There are mainly two kinds of memories: read-only memory and a read-write memory, or it's also called random access memory, where I can write to the memory or read from them. Typically, these are the ports required or the pins required to make the memory work. So there is a chip enabled for to make the memory operation enabled. Output enable is used in case of read operations, read from the memory. There is a data port. So depending on how much what is the width of the memory, the data port will be matching that value. Then you need an address port. So your memory could have this is the depth of the memory, and each location has a width. So to address a particular location, or to use it as an index, we need the address port here, which will be used as an index to address a particular location of the memory. So this is a depth of the memory, and each location is it could be 1 byte or it could be more than 1 byte, depending on how your memory is defined. As we said, it will be a read operation. We can read from the memory or we can write to the memory. ROM is a kind of memory which will be written once or initialized once, and it will act as a read-only memory. So we cannot update or change the contents of the memory. A typical example in a desktop of analogy is this: if you ever notice when you boot your laptop or your desktop, there is something called a BIOS memory where all your hardware related information is stored. What is the hard disk you have, the kind of processor you have, etc. etc. So all that information is in a BIOS ROM, and that BIOS ROM sits on the motherboard. That BIOS ROM is powered by a small battery on the motherboard, which will keep powering it so it doesn't lose that information. So, so that's a simple application of a ROM on the board of a device. Similarly, ROM can be used in other places. If you're doing chip design, typically what happens is in case of FPGA, you have to program the FPGA. Now, to manually program the FPGA always is not possible if you're building a system, an automated system. So what you have is in such cases there is an external ROM on the board somewhere, and that ROM has the FPGA configuration file, bit file stored. On power up, if you reset the board, the contents of the ROM are transferred to the FPGA. That is used to program the FPGA on the fly when you reset your board. So such are applications of ROM, read-only memory, which are used. The contents are used to either store some value or program some other device, or maybe it is used to display some message and boot up an LCD screen somewhere. So there are various applications of ROM. Again, ROM has a similar input lines. The ports are as the RAM. The only thing we don't have is the right port or the right operation. We can only read from the. There are various kinds of read-only memories: a regular ROM, programmable ROM, erasable programmable ROM, or E-square proms as we call them, which is electrically erasable. So most of the ROMs nowadays are E-square proms, which can be electrically erased and reprogrammed once to be used again, to be read again multiple times. Various kinds of ROMs are available. Almost all of this that we use are called are basically, they are volatile memories. They won't retain the values unless there is a power backup somewhere. If the power goes away, the memory loses the contents. So that's a volatile kind of memory. In case there is a power backup, it will retain the contents, then it can act like a non-volatile memory to retain the contents. So RAM is basically a read-write memory. We can read from the memory, we can write to the memory. Data pins, you have RAMs pretty much everywhere, so I don't have to explain to you what a RAM is. It can have a bidirectional port, data port, or it can have different ports for read and write. Typically, there is a control signal, a read-write bar. If this signal is low, this is a memory write operation. If this signal is high, it's going to be a memory read operation. So this is a control signal to denote to the memory whether it's going to be a read operation from the memory or it's going to be a write operation to the memory from external module. Any questions on memories?
No.
Okay. Next state we have next kind of circuits that we have is called finite state machines. Okay, so a finite state machine, as it is called, has a finite number of states, a fixed number of states, and it can basically build any digital circuit using a FSM, finite state machine. It can consist of combinational circuits. It can also consist of sequential circuits, depending on how you want to build it. There is no limitation there. A finite state machine is normally represented by a state transition table, or a state transition diagram. One that you see here is a state transition table. So there is something called a current state, there is something called a next state, there are some inputs, there are some outputs. Depending on the inputs, the current state, there is a reset state. So current state can have one of the states is reset state. And then it goes from that state to the next state of the finite state machine based on certain input combinations. And the outputs are generated when it is in one of the selected states. So each state, depending on what it is, output can be generated in a particular state. So it goes from state to state to state. Again, it will go back, and once the design transition is over, it will go back to the reset state and stay there or wait there till the next input comes. This is a state table. This is a this is a state diagram. So this is simple FSM with two states. So state 0 and state 1. It will go back and forth between state 0 and state 1 depending on the inputs. Okay.
Okay.
Here now we have a four-state machine FSM. There are four states. It is binary encoded. So the states are represented as 00, 01, 10, and 11. So depending on the input combination, this is my reset state. So it will always go back. This is the idle state or a reset state. Initially, the machine will enter this state. From this state, it will go to one of the other states depending on the input combinations. So if input is 1, it will go to state 1. Again, input is 1, it will go to state 3. If input is 1, again, it will go to state 2. If input is 0, it will go back to state 0. The first part is input, the second part is output. So now when it goes from state 0 to state 1, input should be 1. If input is 1, it will go to state 3 and output will be 0. If input is 0 here, it will go back to state 0 and output will be generated as 1. In state 3, if input is 1, it will go to state 2 and output is 0. In state 3, if input is 0, it will go back to state 0 and output will be 1. In state number 2, if input is 1, it will stay in state 2 and output will be 0. But in state number 2, if input is 0, it will go back to state 0 and output will be 1. And again, if you see the idle state, if input is 0, it just stays in the same state until input is 1. So this is the state machine, and it will go from state to state to state depending on the input values. And based on the input values in each state, output is generated as 1 or 0. Okay. So this
Yep.
state machine has 4 states. So these are some basic definitions of state. State diagram is a form of illustrates the form and function of a state machine, normally as shown as a bubble and arrow diagram. Bubble are the circles, arrow is the arrow shown. State is a uniquely identifiable set of values measured at various points in the digital system. Next state is the state to which the state machine transitions to, determined by the inputs present when the device is clocked. Branching, a change from present state to next state. When you transition from present state to next state, it's called branching. And the important part is there are two kinds of FSMs, two types of FSMs that can be designed. One is called a melee machine or a melee FSM. The second is called a mood machine or a mood FSM. Difference is the way it works. In a mood machine, outputs are dependent only on present state. In case of a melee machine, the outputs are dependent on the present state and the input values, the main input values. So mood FSM output is dependent only on current state. Melee FSM output is dependent on current state and the input values. Here is the diagram for the Moore machine. This is the diagram for melee machine. If you see the Moore model, output is dependent on my current state. After the current in the current state, and based on the circuitry in the current state, some output will be generated. In case of melee model, the output is dependent on the current state and and the combination of inputs also. Current state and input will determine the output of the combination circuit, which will be the final output in case of the FSM. So Moore FSM output dependent only on current state. Melee FSM output dependent on current state and input value. That's a key difference that you'll have to remember. You use a lot of FSMs later on in your design, so you have to understand and remember this difference when you design FSMs. Okay. Any questions?
No, yeah, it's totally reminding me of a subject called switching theory and logic design that I've done in like second semester
Okay. Okay.
in my undergrad.
Okay. Okay. Good, you're remembering that. A lot of people don't remember it. That's one of the problems we face when you do design.
It was taught by our dean, so I do remember it.
Okay. So there are more machine diagrams. If we the way the this is called a bubble and arrow diagram. As we see, Moore FSMs can also be we can also recognize whether it's a Moore FSM or a melee FSM by the way the state diagram is shown. In case of Moore FSM, within the same bubble or the same circle, the state value, the current present state, and outputs are shown. So present state value, horizontal line, and output values within the same circle, and the inputs are shown separately. So that will be shown to transition from one state to another state. Sorry. In case of melee FSMs, the state, the circle only denotes the state value, the present state value, and the inputs and output combination is shown in the transition part where the arrow is. Thus, input slash output. So the first part is input or input numerator and output denominator if it's a horizontal line. First is input in numerator, but the next part after slash horizontal or the slash is the output value. So that is how, even if you look at the state diagram also, you can make out whether it's a melee FSM or a Moore FSM. Okay.
Yes. Yes.
Moore and melee FSMs can be functionally equivalent, so there is nothing that a melee FSM can do that cannot be done by Moore FSM. It is just the way the FSMs are designed. They are called Moore FSM and melee FSM. Thinking that the design with either option can be done with the other option. But there are obviously certain advantages of using a particular type of FSM. A melee FSM has a richer description and usually requires smaller number of states. Since the output is dependent on present state and inputs, you need smaller number of states. Smaller number of state means smaller circuit area on the chip. Melee FSM responds one clock cycle sooner than the equivalent Moore FSM because the output will change as soon as the input changes. In case of melee FSM, output is dependent on present state and input. So since it is tracking the input while changing the output change practically immediately or one cycle before a Moore FSM changes the output. Moore FSM has no combinational path between input and output. So Moore FSM is less likely to have a shorter critical path. Um, Mood FSM is the output is dependent on present state, not the input directly. So there is no direct path between input and output. So the timing issues could be even if it has a critical path, it will probably have a shorter critical path in that case. It depends again on the design. This is just a generalization. So FSM, there are certain advantages when you use FSM technique for digital design. It's very simple, it is predictable and deterministic. So you follow a certain methodology or certain steps and you will generate the correct digital design using FSM technique. Due to their simplicity, FSMs are quick to design, quick to implement, and quick in execution. And it's an old representation and system modeling technique. So it's a very structured way of doing digital design. So if you, wherever possible, uh, you should try to use FSM technique for digital design. Typically, you won't go wrong because you have to follow a structured method. You have to follow certain steps in a structured way. So your chances of going wrong in your digital design is reduced compared to if you use some other techniques. Yeah, so now this is a vending machine example which you can relate to, right? So these are the certain conditions given. It can only take quarters and dollar bills. It won't hold more than $1. Each soda, this is a soda vending machine. So each soda will cost you 75 cents. If it is the money deposited is more than 75 cents, you have to return the money. So what are the possible inputs? You can deposit a quarter or you can deposit $1. Then you can push the button to get the soda, and you can push a button in case you have paid more money to return the remaining amount of money. These are the finite states that we can say if you want to implement this using the FSM. These are the finite states, which are basically the currency values 0, 25, 50 cents, 75 cents, and $1. Determine how inputs can change states. So these are my states 0 cents, 25 cents, 50 cents, 75 cents, 100 cents. From 0, I deposit 25 cents, I go to 25 state. Another 25 cents, I deposit, go to 50. Another 25 cents, I go to 75. This is where I can get a soda. In case I don't push a button to get the soda and again input 25 cents, I go to a dollar 100 state. If I directly deposit a dollar bill, I go directly to 100 state. If I'm in 100 state, I will stay in 100 state. If I even put in more money. Soda will be soda will be dispensed either in 75 state or 100 state because at least I need 75 cents. That's the minimum. That's the cost of the soda. So here I can push a button and get a soda dispensed. If for some reason I went further and deposited 25 cents more, or if I directly deposited a $1 bill, I can dispense a soda from the 100 state. I'll still get a soda. But at that point, since I paid more money than the 75 cents, instead of going back to the idle state, from 75 it went back to the idle state 0. From 100 state, I go back to 25 cent state, where I have to return the money back to the user. Every states will return the money and go back to the idle state in case I cancel the operation. So for some reason, user deposited 25 cents, cancel the operation. I moved back to 0 state, return the deposited amount. Go to 50 cents. At that point, the user cancelled the operation. I have to give the money back to the user. Go back to idle state. Any state, if the user cancels the operation, because I have to push a separate button to dispense the soda. Even if I deposited money and I cancelled the operation, I don't want a soda anymore for some reason. I will return. I can return. So return is another button to get the money back. They will always return to idle state and return the value. The money to the user. Each state is encoded in a binary format: 0000001 010 011 100. Okay.
Okay.
Any questions?
No.
Okay. So similarly, we can have a counter. If we, that was a vending machine example. This could be a simple counter which counts from 0, 1, 2, 4. From 2 to go to 4, 5, 6, and back to 0. I can also build this using FSM. So this will be my ideal state. From ideal state, it will go to one state, then it will go to two, then it will go to four, then it will go to five, six. This is somewhere where my output will be generated. Then I'll go back to ideal state. So wherever we see this kind of operation, it can be built using a structured approach like a FSM. So previous example did not include two possible states 011 and 111. If the counter unexpectedly falls into one of the two states, there are two possibilities. The counter will recover by entering a valid state after a finite number of cycles, or the counter will stay in a non-valid state until the flip-flops are reset. So if you see a 011 state is missing and 1117 state is missing. Somehow, if the FSM, the machine or the digital circuit goes into one of these two states, we can have a self-correcting FSM where if for some reason the digital circuit goes into one of those states, it can come back into the previous state, not the next state, but the previous known state, 010 in this case, and 110 in the 111 state. Or the simplest way is in case it goes into one of those other states for some reason, it is not due to the logical operation, but due to some errors or some noise or some other operation, it goes into one of those two states. It can go back to the ideal state and restart executing the FSM. That's a self-correcting way of building FSMs on digital design. Typically, your FSMs or any digital circuit should be self-correcting wherever possible. So, in case the digital design falls into a state which is not a known state, it should go back to a known state. And which is the best known state for any design? It's a reset state, right? The reset state is the known state for all designs. So it can go back to the reset state and stay there and restart your design. Okay, any questions?
No.
Okay, so this is where this is the end of this section, and I will stop here today. So this is what we looked at. We did a refresher of all the digital logic fundamentals, combinational circuits, sequential circuits, finite state machines. Just an overview of everything. Next lecture, I'm going to do a similar overview of number systems, binary number systems, hexadecimal systems, octal, decimal, hexadecimal, binary. Octal, we don't use it anymore, so we'll do a quick examples of octals, couple of them. But we'll refresh the number systems. And after that, we will go to FPGA fundamentals. Okay.
Okay. The next class will be on Wednesday, right?
Next class will be on Wednesday, same time. Yes.
Okay. And